Hello everyone, welcome to Meki Academy. Today we're going to continue with the first chapter for the second part of solid mechanics, which is stress transformation. We did the revision on combined loadings where we create this stress element out of the loadings that exerted on our structure. So for the stress transformation, we are going to learn a few formulas to transform our stress according to the requested angle. So I'll try to stick to 30 minutes video for each uh, explanation for today's lesson on stress transformation. I would prefer to use the same uh, question following up using the same values to solve. But for this introduction for stress transformation, I'll be showing a few formulas that is required and recommended for you to memorize to make your life easier for to tackle this question later. And for this particular one, I'm going to use a slightly different but easier to understand the values, not the from the previous combined loadings revision. But bear with this because the formula that you're going to see in this uh, introduction of stress transformation are the essential ones that then we're going to see also the stress element, the connection between the stress element and the stress transformation equations. So for this example, I'm going to give you a stress element with these values. This is positive value for the axis x, positive x. This is the positive y axis, and the values that I'm going to show over here given this is 20 megapascal of sigma x. The y becomes, the value is negative, the arrow is downward, it is 10 megapascal magnitude, and the shear stress of 30 megapascal shown by the positive tip for our shear stress. So if you are given this element, the stress element, say element A, so in order to transform the stress, so it be involving the degree of angle. So I'm going to show you here if we have a theta of theta, which is this is x prime now. This is where the theta equals to 0 degree is located, and whatever angle for the x prime will be defined as theta right there. So in order to calculate the stress transformation, we're going to use equation, and the fundamental for this, we also need to know if the question given asking you to find principal stresses draw representative volumetric element. The one that you have up here is the stress element, and that is why we are learning the stress transformation, where we're going to define the principal stress, sigma 1, sigma 2. Some textbooks are using the term of major stress, minor stress. And the second question will be maximum in plane. This is a term they are using, which is refers to shear stress. And of course, draw RVE. Now, in order to get, we're going to solve this question soon, and I would like to introduce a few equations which we should know, otherwise it is not going to be solved. So this stress transformation equation, I'm going to put it right here, the sigma x prime equals to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2. Of course, this question doesn't came up from the thin air. It is derived from the formula. So, but for now, we're going to see this. Be careful with the term of 2 theta, sigma x, sigma y in the bracket. They should be justified with the mathematical calculations orders whenever you put in your when you are calculating with your calculator. The second one is sigma y prime is equals to sigma x plus sigma y. It's like y over there, divided by 2 minus sigma x minus sigma y over 2 cos 2 theta minus tau xy sine 2 theta. We have a pattern right here, so plus minus. So take a look, because after this, from this formula, actually it is closely related with the Morse circle we're going to learn in the next subchapter. So so far it is mathematical terms, but by seeing the pattern, you can see what we are doing right here is going to help you when we going to reach the Morse circle subchapter. So last but not least, the tau xy, tau x prime y prime equals to sigma x minus sigma y over 2 sine 2 theta plus tau xy cos 2 theta. So what does it mean by the prime of subscript xy? It is showing that if you are given a certain angle, this is I'm trying to highlight over here. So you're going to put that in the theta, and you will get your sigma x prime, sigma y prime, tau x prime, y prime slanted at an angle. You're going to see the example. Actually, you can use the previous example, but for this particular one, we're going to use the simple like as element A up here. So in order to solve this, so this solution, you're going to first of all define local axis, which we already did, positive x and positive y. And second step that we should do we need to define the stresses for the for that stress for element A. So we can easily identify right here sigma x is equal to positive 20 megapascal, because that is what it is by seeing the symbol. The direction of our arrow is going outward to positive x. Sigma y is equals to negative 10 megapascal. This is what we are using because the arrow is going downward towards the stress, as if it is in compression, so the value is negative 10 megapascal. You don't have to put the negative sign for the stress element, because it is the present state. It is correct way of showing it is actually 10 megapascal. So it is equally important to know that. Then last but not least is our tau xy equals to that is positive, obviously the 30 megapascal. So we have identified the stresses, right? And the third step, we're going to define the principal stress state. And I've written 3 equations up here showing that this is our fundamental equations that we need in order to solve for our stress transformation. Together with this equation, we also going to need the calculation to calculate our principal stress angle and shear stress angle. So I'm going to write it down over here. So yeah, on the right side, I'm going to list down all the equations, and we're going to calculate that later. Alright, so it is essential equations. Tangent to theta p refers to principal stresses. The equation is 2 tau xy over sigma x minus sigma y. And another equation is also, we need to know 2 tangent to theta. S refers to shear stress, equals to negative sigma x minus sigma y over 2 tau xy. Recognize the pattern. It is slightly different, but the fundamental is the same. And both of these coming from, I think this is the last equation that we showed. Yeah, of course, I will say to you guys, should be remembered in order to solve the stress transformation, the very first chapter for solid mechanics 2. So here we have maximum shear stress. The formula for this is tau max equals to square root of sigma x minus sigma y over 2. Everything is in the bracket, power of 2 plus tau xy square. So we've got everything written down, the formula for stress transformation, and for the probably we're going to see the solution straight away for principal stress state. So we can by using the formula that we already written on the right. So we can say here tangent to theta p is equals to 2 tau xy over sigma x minus sigma y. So by plugging the values, so we have already the values that we identified in step 2. So 2 of 30 megapascal divided by 20 minus 10. Be careful with the negative sign for that sigma y. The unit is similar, megapascal. Here we will get, alright, continuation from this, tangent 2 theta p is equals to right 2. So it comes to 2 theta p equals to 63.44 degree counterclockwise, and the other angle is 243.44 also counterclockwise. Theta p, we divide everything with 2, so we will get 31.72 degree and 121.72 degree also counterclockwise. We're going to see this. There are two answers for that. You can leave the answer only one also can, but when we go to the subchapter for Mohr circle, we're going to see these two angles more pronounced because they are located in the same plane for sigma x, sigma y. One angle is one point is the x location. Stress on the x-axis is 180 degree to that location is the another angle. We're going to call that alpha and beta soon, but for now we are having these two values for tangent to theta p. So theta p, principal stress, the angle is 31.72 degree and 121.72 degree. So by having that values, by taking to the equation, so the state of stress for the principal stress, there we already calculate the angle, and by the question for this particular example, they ask the principal to define the principal stresses. Right, for the I haven't shown the principal stresses. This is the first time that we're going to the calculation for principal stress. Yet another formula, principal stress. Sigma 1, 2 is equal to sigma x plus sigma y over 2 plus minus square root of sigma x minus sigma y over 2 square plus tau xy square. So I should put this in the box because this is another important formula in this series, right? So so we can straight away calculate this. Sigma sigma 1, 2 equals to 20 plus negative 10 over 2 plus minus 20 minus negative 10 over 2 square, the square bracket, and 30 square. So we can project our answers in sigma 1 comma 2 is equals to, by simplifying the equations that we have just now, 5 plus minus 33.54 megapascal. So basically we're going to have two answers. One is sigma 1 and another one is sigma 2. uh, do the math for this. This is 38.54 megapascal, and another value is going to be sigma 2 is equals to going to be negative value 28.54 megapascal. So you're going to call this major stress. Together with that, we're going to have our major theta for this 31.72 degree. This is we're going to call minor stress. Minor stress. So this is our theta P2 is equal to 121.72 degree. And the direction for these are both counterclockwise. So by having that, we already calculate the principal stresses, sigma 1 and sigma 2, major and minor stresses, and we can calculate the RVE. So by having the RVE for this, I'm going to draw first of all um, the theta 0 degree theta for this stress element, and by taking this this answer, so I'm going to draw my slanting angle of 31.72 degree, and by having that reference, you can draw your the box for the RVE, which is 90 degree perpendicular to that blue line. Right, and so you can finish the stress element for this. That is the angle 31.72, and the value for right, this is 38.54, the principal stress 1 megapascal. Similar on the opposite direction, and the negative 28.54 is going downward on the stress element with the value of 28.54 megapascal. So this is the answer for question number 1, principal stresses, and draw its RV. And so what is the purpose of this stress transformation equation right here? So what the equation is supposed to do is to, if you plug in the values of 20, 10, and 30 in it, you're going to get your it is vice versa. Actually, the process is the by using this formula for principal stresses, you're going to get your values of 38.54 megapascal. By reversing that process, you take the value of when you from this value, if you put in the stress transformation equation, you're going to get back your 30 megapascal for shear stress, 20 megapascal for sigma x, and negative 10 megapascal for sigma y. So if you can continue to solve the second question, maximum in plane shear stress. So right here we have maximum in plane shear stress. The process is just by taking the formula that we have written before. Tau max is equals to sigma x minus sigma y over 2 square plus tau x y square, square root of this. By having that value, we have tau max is equal to, right, we've got 20 minus 10 plus 30 square. So it becomes the total of this, when you calculate, we have maximum in plane shear stress, tau max is equal to 33.54 megapascal. That is our maximum in plane shear stress. Right, so this is maximum in plane shear stress. So maximum in plane shear stress. I would like to show this equation again when we calculate the principal stress. We put in the form of sigma 1, 2 is equals to 5 plus minus 33.54 megapascal. This is in the form where the whole equation that I've introduced in the beginning, the formula is sigma 1, 2 equals to sigma x plus sigma y over 2. The first bracket refers to the sigma average. We also call that sigma average, sigma x minus sigma y over 2 square plus tau xy square. The second part is I highlighted in red. This part is the one that we maximum in plane shear stress, and the first part of this equation is the sigma average. Understanding this equation is going to help you in this later part of this chapter, more circle. So we haven't finished with the maximum in plane shear stress because the question also asks the draw the RVE, the representative volumetric element. So for this, in order to draw a perfect, correct RVE, we need to know the angle also, and this is where the formula of tangent 2 theta s is going to be useful, which is this is negative sigma x minus sigma y over 2 tau xy. So by calculating this, you will get tangent 2 theta s is equal to negative 20 minus 10 over 30. You gotta get negative half. 2 theta s is equal to 26.56. It is 26.56 the value is clockwise and 153.44 degree counterclockwise. Double checking that value. So theta S equals to tangent 226.56 shift tangent of negative 0.5 will give you 26.56. So the shear stress for both directions are the same, which is the value is the same, where the sigma average, the value of sigma average. So theta S divided by 13.28 degree and 76.72 degree counterclockwise, and it is more obvious when we draw the stress element on the by using the reference of theta equals to 0 degree, and this is positive. 13.28 is going slightly downward. This is 13.28 degree. This is x prime, and by using as the blue line as a reference, draw which is 90 degree to this blue line. Draw your element rectangle, then you can finish up with all the values for shear stress for the element. And for this value, this is 90 degree to that x prime. You have your y prime. This is your positive y. So this is the value of 5 megapascal on, they are equal on x and y direction, 5 megapascal for shear stress, and the tau maximum is equals to 33.54 degree. Sorry, 33.54 megapascal. And no, we have pointed the 13.28 degree, one of the angle, and the second angle is this 76.72 degree from the theta equals to 0 degree line. So this example, as an introduction for stress transformation, we have calculated and drawn the RVE for both questions, maximum in-plane shear stress and draw is RVE. We have done that, and this is I'm using the slightly different values just to show the connection between the stress transformation equation, how to use the equation for principal stress and maximum in-plane shear. And I believe this is the first time you are seeing this formula, which is very important. We're going to use the similar example with the values that we have from the previous revision for combined loadings in the next video. Thank you so much, and you can have a look, digest the equations that you have seen today, and try to make sense of that, and let me know if you have any questions. Thank you very much.